they're labeled from 0 to n-1 and that they're linked right and all the rest of this stuff. So if you can check it, do. That's sort of that should be your mantra whenever you're dealing with their kind of with R and I graph and the rest of these. All right, so it's useful once you have these data to do something with them. And so the first thing you want to do most of the time, other than plot it, is calculate some metrics. And what I refer to as metrics are just any score on the graph. And we're going to talk about two classes of metrics today. We'll talk about more throughout the course of this semester or this workshop, but we're going to talk about, I guess, three types here. Some basic reachability features, just some volume features of the network, some very simple things. Reachability and path structure, that's the thing that makes a network a collection, a system. And so those are the features we're going to talk about there. And then centrality, which is probably arguably the most commonly used metrics on the network. So you've seen this already. This is the simple adjacency matrix. The basic volume features that people care about are first the size, which is just the number of nodes and the number of edges. And so in this case, you have 5 nodes and 5 relations in this little graph. And then the main volume feature that people tend to care about is something called density. And density is the average value of the adjacency matrix. It's the average value of edges across all relations in the network. For a binary graph, it's the probability of a tie on any randomly chosen dyad. So that's what it would be. For a valued network, the probability doesn't make sense. It would be it's a mean essentially. But so in this case, for a valued network, you would take this entire network, and you would just sum up all the values and divide by the number of possible ties. Notice that it's 5 times 4 because we ignore the diagonal. We don't care if people like themselves or not. We hope you do, but it's irrelevant for most of our stuff. Degree, the problem with density is, and you guys, this is pointed out above here, the problem with density is that the number of possible ties ends up scaling much faster than, so the denominator ends up growing much faster than the numerator. And so if you have a density measure and you're comparing two networks, it's really hard to know if the issue is that one network is just bigger than the other or if the density is actually different. And so density is a pretty hard to interpret number across different sets. And so what we typically use is average degree. And degree is the number of other nodes adjacent to or incident to your focal node. So it's the number of ties a person has in a binary network. And so each person has 2 types of degree in a directed network. You have your out degree, which is the number of ties you send. And you have the in degree, which is the number of ties you receive. As you might imagine, right? These are, it's just 2 different ways of summing across either the rows or the columns. So the sum of the out degree has to equal the sum of the in degree. So in this case, there are 7 overall linkages, valued linkages, directed linkages. Once you have an edge, if it's a directed network, you want to know whether the network is reciprocated or not. You might imagine that this is relatively easy, but it turns out there's a lot of different ways of calculating reciprocity in a network. The standard measure is to break your network down into, for each dyad, whether the dyad is mutual, like this one, whether it's asymmetric, like A to D, or whether it's null, like C to E, there's no tie at all. So the distribution of mutual, asymmetric, or null dyads on the network is the dyad census. It's the categorization of all possible directions of dyads in the network. And the global reciprocity is just the number of mutual over the number of mutual and asymmetric. So that is the proportion of all the observed non-empty ties that are reciprocated. But when people think about reciprocity, we tend to think about it from a person-centric idea. And so we would imagine that the ties reciprocated is that of all the ties sent, how many of those are also reciprocated? And that's a slightly different number. So in this case, you see that there are 4 ties that are reciprocated out of the 7 total ties sent. So that is, this tie is sent, and that one is sent, and that one's reciprocated. Those 2 are reciprocated. These ones are all sent but not reciprocated. And so in this case, you have 4 reciprocal arcs out of 7 total arcs. And so the arc reciprocity is 57%. Both of these numbers are kind of interesting, right? So we can have a debate over a beer whether or not 57% is a high reciprocity rate or a low reciprocity rate. Most people would say, well, it's compared to what? And so compared to what is what this little row measure is. Rho says, well, let's compare it as flipping coins at random. And so if we were to take every dyad and flip a coin, make it symmetric or not, given the total number of ties in the network, we would expect that this is 38% more than you'd expect by chance. And so the formula for that is here. I'm not going to go through what it is, but rho is the chance-adjusted probability of having a reciprocal tie. Now, a degree distribution is a network level statistic, and that's for each node has a degree, the number of people they're tied to. And the classic degree distribution in a social network is scale-free, or it has this really long tail. So if you plot it like this, it's impossible to see really what's there. And so you typically plot it on a log-log scale. So we have the log of degree and the log of the count. And the characteristic signature of a power law distribution is that it's a straight line or close to a straight line in the log-log plot. And what this is really saying is just that there are most people, the vast majority of ties, people have very few ties, but a few people have a whole lot of ties. And you can't, and that feature is something that we found in almost all networks. So sexual networks, friendship networks, if you let people know, the number of authors you have or co-authors you have, most people have a few co-authors, but a few people have lots and lots of co-authors. The thing that makes it interesting about a degree distribution is that the people who have high degree are also often stars or hubs in the network. And they're responsible for connecting the overall graph. And so if you know which nodes are the hubs, then the removal of those nodes or the suppression of their ability to pass things ends up disconnecting the network. This is a big deal in the 80s and 90s when people were first thinking about sexual networks, because as you might imagine, if you wanted to stop the distribution of something like HIV, you want to focus your energies and attention on the people most likely to hold the network together, that is the people most likely to spread disease, and so you want to get people with high degree to use condoms or other kind of prophylactics to stop the movement of an HIV. And this, for example, is from Colorado Springs. This is some of that data that Rich Rothenberg and John Potteritt collected, and these are all commercial sex workers in Colorado Springs, and they're Johns, and you can see, for example, the commercial sex workers tend to have very high degree, but in this case, they're not necessarily the hubs of the network. It's their Johns and their drug dealers that are the ones who are pulling the rest of the network together, because in this particular context anyway, the commercial sex workers were pulling in people who weren't themselves otherwise connected to others in the network. So their high degree didn't really correlate with being a hub in the network in the sense that we had it here. The thing that makes a network a system is the extent to which the ties link to other ties, right? And that sort of binds the entire thing together, the entire community together. And we refer to this as connectivity. And there are three features of connectivity we're going to talk about today. One is reachability. Is it possible to get from one part of the network to another part of the network? The second is, given that it's possible, how many steps do you have to take? What's the distance? And the third is, how redundant is the linkage between any two parts of the network? So do I have a single path that I can get you? Like I'm stuck on I-5, or can I find myself a way around the city? Right? And so those three things all connect different parts of flow in a network. In order to get connectivity, you need a concept called a path. And so a path in the network is essentially is where you start with one node, you follow an edge to land on another node, follow an edge, land on another node, and keep moving. There are lots of different flavors of paths. There's walks, there's circuits. We're not going to worry about the distinctions between those right now today, but by and large, you need to think about the system of paths, because that's what's going to decide whether a network is reachable. For reachability, the key is that you want to take any network and sort of follow that path as far as you can. And so that's what's known as a component. A component in a network is a set of nodes, the maximal set of nodes, for which if you were to trace all edges going out from any node of the network, you would reach every other network. It's the end of the set. You can think of this, another way to think of this is the connected sets in the network. And so in this particular network, there's one giant component, that is, it's a component that contains more than 50% of the nodes. It's known as the giant component in graph theory. And then lots of little components. So there's a bunch of 3 components, a few 4 components, a handful of 6 components, but those are all the small ones. And so what's not a component is like this little chunk right here. That's a part of the network, but the component is maximal. It's everyone you could reach from that set. Now it turns out that there are 2 flavors of components. You can have what's known as a strong component or a weak component. A strong component respects the directionality of a graph, of the arrows. And so in this case, The red component there is one strong component. If I start in the upper top, I can follow the arrow down, over, and come back. And so that all four of those nodes are reachable both from each other, right? So the entire directionality is the same. Whereas this white node, I can't, once I go here, I'm stuck. I can't get anywhere else. So that means there's no one in the red node can reach the blue node, or they can reach it. In that case, they can't. They can't get back. In this case, the blue node can reach the red node, and once they get there, it's stuck and you can't get back. So a strong component respects directionality, and in this case, there are two strong components of size 4 and a handful of little components. And a weak component just ignores the direction. It says, let's just focus on the edge as if it were not directed. Components are interesting, because components are the limits for disease diffusion, right? Or any diffusion, but disease is what we're often interested in. And it turns out that there's a strong linkage between the degree distribution and the component distribution. If you imagine a degree distribution in sexual networks for a health process, for example, you could have a network where you have, most people have very few sexual partners. So in this population, most people have 1 or 2, a handful of people have 3 sexual connections, and the average is about 1.68. And if you were to simulate a network, given that sort of degree distribution, out of 10,000 nodes, the largest component would be about 200, and it has this kind of really spindly structure. So if a disease found its way in here, if any person along the chain stopped the transmission, either due to random chance or using a condom or some such, then you wouldn't get the disease to pass very far. So these are pretty safe networks with this distribution. If we were to shift it a little bit and take some of the people who have a degree of 1 and give them a degree of 2, you end up with an average going up to 1.74, and now you get a little more connectivity. Shift a little bit more, a little more, a little more, like this. Now notice that you've shifted from 1.68 to 1.8. So that's an average shift that you wouldn't really pick up within the standard error of most standard surveys, right? You wouldn't know you had the difference. But the difference in connectivity moves from 200 to almost 6,000 in this population. And most of those nodes are reconnected in that red set. They have a redundant set, which is called as a bicomponent. And so what that is known as in graph theory is the emergence of a giant component. And almost every network, depending on the shape of the degree distribution, has some tipping point, some phase transition where you move from almost no one connected to almost everyone connected. And as you might imagine, I cheated. And the phase transition here is right at about 1.7. So I picked a few nodes on one side and a few on the other, and you shifted it to the other side of that. Knowing where the phase transition is in your network will help you understand whether or not your setting is one where you have to worry about the spread of disease or one where you don't have to worry about the spread of disease. Giovanna Merli, who's a co-PI on my training grant here, and I once simulated all the sexual networks in China and Shanghai, and we were able to discover that it's very unlikely that those sexual networks would be on the far side of an emergent component. So the chances of a generalized HIV epidemic in a place like Shanghai are incredibly low, given the structure of the networks. So that's the kind of thing you can do once you understand these features. All right, so connected or not is the limit of spread on a network. Once you have the limit of spread on networks, you want to know what's the likelihood of spread. And so the likelihood of spread tends to go down with distance. The further away we are, the less likely we are to share something. And so we calculate distance usually with what's known as geodesic distance, or the breadth first distance. So you start with A, you find all of their peers, and A has 4 people 1 step away from it. These people are 2 steps, 3 steps, 4 steps, and 5 steps. And so the diameter of this graph is 5 steps. The maximum distance from A is 5 steps. And you have some people that are close, intermediate, far, and farthest. You'll notice a handful of these edges, these are known as transverse edges. These are reconnections at the same distance, but they don't reach any new people. Distance is also directed. It's a problem with switching slide decks. This should look like a matrix, but my font, my monospace font disappeared. That's kind of odd. So anyway, you can think of a distance matrix from A to A, for example. In a directed network, the distance from A to C is going to be different from the distance from C to A. So it follows the directionality of the person. In this Colorado Springs example, the 695 people in this set, the longest passed in this network is about 17 steps, and the average distance is about 5 steps, right? With 75 people being within the 3-step orbit of the average person in the network. Yes, please.
So can I ask, so by distance, like physical distance, or like what is each step represent?
Yeah, so the distance is the number of hops.
Oh.
Yeah, so literally right here. So everybody you're directly connected to is distance 1. Everyone, their direct friends who are not friends of yours or not contacts of yours are distance 2, or wrong direction, or distance 2. Those are distance 3. Those are distance 4, and that would be distance 5. Have you ever heard of the 6 degrees of Kevin Bacon? That's the distance, right? So so 6 degrees of separation. That is geodesic distance. The thinking is that that's the number of hops you'd have to go through to reach someone else. A geodesic distance has this characteristic where you're starting with one person and broadcasting out to everyone they could reach, and so it gives you the shortest possible distance in terms of number of steps from A to anyone else. Most diseases or information or whatever don't know the shortest distance, and so they're not going to be able to follow the geodesic distance. And so the shortest distance we use, because it's easy to calculate, to be honest, substantively, you're often going to want to use what's known as the random walk distance. So you would imagine that a person, got a disease, they're just going to randomly flip a coin whether I go down this side of the path or that side of the path. And so the random walk distance is another flavor of distance. There's some weighted distances that are based on the strength of the edge, for example. So you can tailor this depending on what kind of process you're dealing with, but the distance is always some function of the number of edges you have to go between me and you. Does that make sense? Awesome. All right. It turns out, just if you're curious, that most networks, geographic distance and social distance are highly correlated. That's just good fact of the day. So now we have reachable or not. So is it possible for me to get to you? If so, how many steps does it have to take to get to me from you? And now the third element relevant for disease diffusion of some sort is usually how redundant are the paths from me to you? Is it a single path or are there multiple paths? And so that tends to be measured in terms of this thing called transitivity, so at the local level. And so here you can imagine the ego has one person tied to all of their altars. And so in that case, there are no redundancies. The altars are not tied to each other. In this case, ego is tied to those same people. Some of them are also tied to each other. So that creates transitivity, that a friend of a friend is a friend, is a transitive tie. And so a transitive tie means that if I get to ego, and I get to altar, or if I get to these two folks, odds are good they also get to each other, and so whatever's happening here is going to circulate. In this case, if something gets to here, it has to go back through ego before it can get to altar. So redundancy creates these possibilities to create new transmission routes, to go around bottlenecks in the network. Now that's true at the local level, but it's really important at the global level. The key to this, of course, the first foundation is components. And so in this first graph you see here that you have one component and a second component. But it turns out that this redundancy we can think of in terms of cut nodes of a graph. And so in the first case, if I wanted to reach from the top of this graph to the bottom of the graph, there's a single node that is a cut node in the graph. If I were to remove that node, it would fall apart. In this case, if I want to get from the top of the graph to the bottom of the graph, I have to remove 2 nodes to separate these things, so that it's what's known as bi-connected or 2 connected. So that means there's no way that I can block the flow from A to B without stopping it at least 2 separate nodes. And that's nice, because that means that no single node can control the flow of information or goods or what have you moving across the network. In this case, this node has a lot of power, right? So if you're this node is a broker from the top to the bottom, and the bottom can't interact with the top except through the bottom, except through this key cut node. In this case, information or whatever can flow around. And in this case, there's 3. There's an interesting mathematical feature here, which is that the number of cut nodes is also equal to the number of node-independent paths in the network. This is just a mathematical theorem. And so there's this nice cohesion feature, when you think about the flow of information or goods or some such, that there's a direct analog between the number of nodes you need to remove to split the graph and the number of unique ways you can traverse a graph. So as a general principle, the higher the connectivity of the network, right, the easier it is for things to flow through that graph, right? Because nodes can't stop something from moving. Does that make sense? Awesome.
What is the definition of splitting or disconnecting?
Yeah, so the definition of splitting would be if I remove the node, how many pieces are left over? So in this case, if I were to remove this node, it's still a single component. If I were to remove this node, you'd have two separate components. And we can algorithmically figure that out. I know which ones are which because I can look at the graph and see it. There's a feature called max flow min cut, which it's an algorithm that lets me go through and identify which nodes, if removed, would separate the graph. And I can do it for nodes, which is what I'm describing here. You can also do it for edges. I can say if I remove this edge, what would happen if we remove that? So that you can be both node connected or edge connected. And these are two different ways of getting at that. But the key element is the opposite of cohesion is fraction. And so if you want to ask, the nodes that are difficult to cut apart or difficult to break up are going to be more cohesive than nodes that are not.
Parts need to have more than one node in each. What if I cut two ties and then it's still the same graph and then one additional node that's isolated?
Yeah, so if I were to remove these three nodes and just have this to myself, that would still be disconnected.
Okay.
But it's sort of substantively not very interesting. Right. Yeah, so that's actually, it's a little bit of going deeper than we want to, but it's every node, the cut set for any node is equal to its degree, right? So any node that has 5 ties can be separated from the graph if I remove the right 5 people, right? But for a graph as a whole, we can say this graph is essentially more fragile than this graph, because in this case, I have to remove only one node. In this case, I have to remove at least 3. Now, cohesion, it turns out, in a network, and so we've proposed this as a measure of cohesion, or what we call structural cohesion. Turns out there's a kind of an interesting feature of it, which is cohesion is rarely homogeneous across the entire population. Some parts of the graph are more deeply connected than other parts of the graph. And we refer to this as cohesive blocking. And so the graph as a whole, in this case, is not connected. The connectivity is 0. That's what the K stands for. And so that's because these two nodes are isolated. Right? So they're off in their own world. The rest of the graph is over here. But then embedded within this whole graph are 2 components, one little of size 2 that is one connected, and another node. In this case, it's bigger. I don't know how big this is. K equals 1. And it's K equals 1 because if I were to remove this node, or this node, or that node, right, they're linked to this graph by a single edge. So those nodes are cut nodes for the graph as a whole. But then embedded within that are slightly more cohesive sets, and embedded in that are slightly more cohesive sets. So you can decompose any network into these subsets that are more deeply embedded within the graph. And those graphs, by being embedded, it means that they have lots of opportunities for sharing ties. And if things come out, they come back to themselves. And so the only way to isolate these graphs, or the simplest way to isolate these nodes in the network, would require you to dig deep down into the structure of the graph. That's what we mean by embedded. They're deeply inside the network. These nodes are peripheral, these nodes are embedded. And every network has this kind of an embeddedness structure. And that's interesting because you can use your depth in this structure to think about how much you know about the network. And that's one theory says that the people that are deeply embedded are the people that really know the network because they're living it every day and they're sort of engaged in all these different parts. And all the flow has to move through them, right? So there's lots of different circuits that are going to come around and flow through these networks. Another theory says that people on the outside are better observers. They have more time to look and to watch and to see what's going on. And they can see what's going on amongst the people who otherwise are busy living the life of the network. And it depends on your context, it depends on your setting, upon which of these is going to be more or less true, but you can write a good theory about why it would be the case that embedded nodes might feel more a part of the society or more part of the community or something like that. Please.
So how do you identify the group that is most embedded the level of depth?
Exactly. You do exactly this process that I outlined here in this tree. You find the 0 cuts, remove those nodes. Find the 1 cuts, remove those nodes. Find the 2 cuts, remove those nodes. As you keep doing that, the network gets smaller and smaller The ones left over at the end are the most embedded. Yeah. So it really is a recursive process. I mean, you don't actually go to the group and remove them, right? But algorithmically, you go through this structure of the graph and you identify the nodes that, if removed, would break it apart. So you're cutting, as Carter Butts likes to say, you cut society, you cut meat at its joints. You find the weakest points in the setting and you break it there. Then you find the next weakest point and you break it there. And you keep doing that over and over again, and the pieces left over are definitionally not the weakest. And so those are the ones that are the most deeply embedded. Please.
Are 7 and 8 then the same level of depth? The most embedded?
Yes. In this case, these are both, they're the most hardest to get to. There are 4 cuts into the graph. One is a little more connected. It has a k equals 3. The other has k equal 2. They're at the same depth. Please.
Can you explain one more time what the K represents?
K is the number of nodes that you would have to remove from the graph to break it into more than one piece.
So I guess 3, where it's circling all of those. Yeah.
Yeah.
Level. Oh, okay. I see the lines now. The
Yes.
lines are hidden by the other lines.
Fair enough, yes, yeah.
Okay.
That's the problem with this set, yeah. So here is k equals 0 because it's already disconnected. Here you have 2 sets of k equals 1. Here you have, and within the largest one, you have 3 more sets of k equals 2 or better, and then k equals 3. They're all nested inside of each other. It's kind of we like this measure. My Doug White and I spent a lot of time working about this, and it ends up being fairly predictive of some interesting things. So that's cohesion, right? So that's the cohesion. So far we've now done volume, which is degree and density, and we've done cohesion, which is the number of paths that relink and the ways and the distance between them. You could do a lot in networks with just that. If you want to go out and make money in the police department, you can identify the cohesive structure of gangs, for example, and figure out who's been arrested for who, and you can get jobs doing what's known as link analysis in most major police departments in the country, right? And that's it. You can walk away now and do nothing else. If you want to do more, right, the next thing you want to do is identify sort of individual variance in your embeddedness in the network. And embeddedness used loosely here. And the common term for this is something called centrality. So centrality in a network is the idea that some nodes are going to be, this picture might work just fine, that some nodes are on the edge, so they're not central, and some nodes are on the middle, and they are central. And it turns out that there are lots of different ways to measure centrality, because there's lots of different ways to be on the outside versus to be in the middle. And so these are big multidimensional graphs, and you think about something as like a little graph I showed you a minute ago is what's known as planar. It fits nicely on the page. But real graphs don't. They're this bumbled hairball mess. And so we want to find different ways to think about being at the middle versus being at the edge. Now there's something of a growth industry in inventing centrality measures. I'm going to talk about 4 of them. I'm going to talk about these 4. There are a lot more out there. The standard joke in networks is if you want to make your name in networks, invent a centrality score, right? So that's what's left. We're going to talk about 4 of them. These are the classic centrality measures. We've already talked about one of them. It's degree. And then we're going to talk about these others in a second. But just know there's a lot of them out there. And you might ask yourself, why are there so many centrality measures? It's because centrality is implicitly a theory. It's a theory about what matters in the graph. It's a theory about how the pattern of relations affects some behavior. Most of the time, our theories have to do with the flow of goods. We think that might be that people who have lots of ties are influential. If that's my theory, then degree is what matters. If instead, I'm a Ron Bertian kind of person who can think about the ways in which I can control the flow of others, then being between lots of others, to be in the middle of lots of flows matters. And how you define the flow, how you define being in the middle, all these other things are different theories. But some people look at a thing like this and go, I'm done, I'm out of here, this is all I can take. I think that's the wrong reaction to this level of variability. This is your opportunity, right? You shouldn't be constrained by the fact that, well, closeness centrality didn't work. Well, closeness centrality might have been the wrong theory, right? So what you want to do is say, what's my social process? Go back to that multi-level graph I put out before. Whatever your behavioral assumption is, what you think drives people's behavior, you can map that to micro-relations, and that will give you a centrality score. And there could be lots, you might end up with your own, secret centrality score, the people most likely to tell a secret to somebody else. Right? If that's the theory you think that matters most for driving behavior in a setting, then define the process that links secrets to structure and measure it, and that's your score. And that's all this is. What you're seeing is the history of that being done across lots of different settings, and we're going to give you the general ones to start with. So I'm going to start through the next 4 or 5 slides are all going to use the exact same pictures. So we have a couple of end cases or liminal cases. The star graph, in a star graph, for any measure of centrality to be a centrality measure, any centrality measure should have the case that in a graph of this structure, the hub should have the maximal value and the leafs should have the minimal value. All right. In a circle graph, over here, each node is indistinguishable. Right? So everyone should have exactly the same score. For any measure I come up with, because every node is exactly equivalent, it should have the same score. In this case, there's going to be some variance. So this node will be different than this node, will be different than that node, because they have a differential pattern in the overall network. I'm going to explain how in a minute. And a line graph is the same kind of idea. There's lots of different ways to write the sort of formula for this, and it's, again, it's the part of the jargon of the business. I wouldn't worry about that too much right now. Degree centrality is the one that I've labeled the nodes with here. So degree centrality is just the number of nodes adjacent to me. So in this case, this person is adjacent to 7 others. This person is adjacent to 1. This person is adjacent to 3. This person is adjacent to 3. This person is adjacent to 2. If you think intuitively, centrality is in the center. Centrality is in the center. The person in the center should have the biggest centrality score. Then you look over here and you go, wait a minute. This person's in the middle. They have a nice big centrality score of 3. But this person's at the edge, and they also have a centrality score of 3. That's not right. That's because degree is a local centrality score. It's just the number of ties I'm tied to. As far as degree is concerned, the rest of the paths don't matter. That might be good. If your theory is a local theory about sort of local contact, then that's important. If it's not, it's going to give you some kind of a mixed understanding of the network. I did this little made-up graph just to drive the point home, right? So in this case, the node that's tying the whole system together actually has amongst the lowest degree centrality. And so it's the pattern of ties that matters in our heads, but a degree measures the people that you're directly tied to. Now, some theories, degree really matters. So if you care about, I think particularly for negative ties, so if I care about whether or not people are bullied or not, the number of times that I've been bullied might really matter as an individual behavior. And the fact that I've been bullied by somebody who's also been bullied is much less interesting. But for information flow, it matters. All right. Once you have a centrality score on the node, you can characterize the system by centralization. So centrality is an individual level score. Centralization is a system level score. And it tells you the inequality and the dispersion of centrality. You might think, well, there's a whole set of things. These are Freeman centralization scores. And what Freeman does is he takes the observed score minus any observed score from the maximum score and normalizes it. It turns out that these centralization scores are really hard to compare in lots of ways. I actually prefer just the variance. Like we have lots of good dispersion measures. The classic variance measure works just fine. So either of these work. You can do whatever you want. I'm going to give you the formulas for all of them, and you'll see them in the literature. But essentially, centralization is the distribution of centrality in the network. All right, so degree is a simple one. We already have that. It's out of the way. Let's now think about the degree centralization scores. Sorry, that's on here. So in this case, the degree centralization for the Freeman centralization is perfect. That's because the star graph, it has to be perfect. And the circle graph should be 0. And that's because if you were to take, this is the maximal possible the most centralized a graph can be is to have a hub and spoke structure. In this case, you'll notice that the centralization is really low, right? Even though it kind of looks like a star graph. And again, that's because it's a degree centrality score. So because it's a local score and most people have 3s, and this is a network full of 3s, so there's very little variance. Now let's think about a measure that takes the path structure into account. Closeness centrality is a measure that uses that distance measure we talked about before, the number of hops between people. And it says a person is some average number of hops from everyone else in the network. That's what this D is. So the distance from person I to person J is just the number of hops it takes me to get to Lane. And so I go from Lane to Gabe, from me to Gabe to Lane, that would be 2 hops. We take that and we sum that up across from ego to all possible other people in the network. Right? So Moody to Gabe, Moody to Lane, Moody to Dana, right? So I go over to all possible people in the network, and I sum up how many steps it takes me to get from each of those people. That would be the farness. Right? That would tell me on average how many steps I have to take to reach everyone else in the network. And then I might want to do something like, normalize that or something in a minute. If we take the sum of the distance, because we want to take people, we would like to have a number that's big when people are at the middle, we invert it. So we just flip it around. So that says how close I am to someone else. It's the inverse of how far I am to someone else. I thought I had it on one page, I'll put it here. So this is an example of what that would look like. So the person in the middle is our first person here on the top. And so that person is 1 step from everyone else in the network. So you sum it up. So they're 1 across everyone else. You average that out, and that tells me that they have 1/7, which I believe is 0.143. Whereas everyone on the edge, they have to go, they're 1 step to the middle, and then 2 steps from everyone else in the network. In the circle graph, each person is 1 step from 2 other people. There are 3 steps from a few more and 4 steps from a few more, but if you go through and look at this, you'll see that every person has the same set of numbers, just ordered a little different. Right? And so this is why everyone has the exact same distance to everyone else. A line graph makes it pretty easy. Here you can see that this person in the middle has the fewest number of hops to reach everyone else in the network. Right? So that would be it's the person right here. This person is the maximal number of hops to reach anyone in the network is only 3, whereas the people on the end are at least 6 hops from 1 other person in the network. So their distance is further. And so this sort of scales nicely. So the person in the middle has the highest centrality score, a little lower, lowest. Now a little kite network, you can see that again, people on the edge here have the lowest centrality score, a little higher, and highest. Right? So these are the people that are the most into the network because they can reach everyone else quickly. Closeness centrality is what's known as a radial centrality score. You can think of it matters in situations where you could have kind of like heat. Like I'm sending out a broadcast into the world telling stories. My friends pick up those stories, they tell it to their friends, and it moves out, and it just sort of radiates out through the network. And people with high closeness centrality have the ability to broadcast to more people with less effort. That's the intuition behind closeness centrality. This closeness centrality is based on geodesic distances, on that shortest possible length between everyone else. You can have a closeness centrality based on random walk distance. You could have a closeness centrality based on a limit of weight. So there's lots of different ways you can define your distance and then define a new closeness centrality, but the traditional one is based on geographic distance. The final measure is known, the final centrality is where the final of the classics, there's one more coming, but the third one is this thing called betweenness centrality. And betweenness centrality says a node is important because it can interrupt the flow from someone else. So in order for B to reach anyone else in the network, they have to go through A. In order for C to reach anyone in the network, they have to go through A. So A is between everyone else in the network. And that's exactly what betweenness centrality measures. Betweenness centrality says, for each person I, let's look at every other pair in the network, and let's find the shortest path between that pair, and then ask, is I on it? Am I on the shortest path between Lane and Dana? If I am, I'm between them. This score goes upwards. That essentially says I have the opportunity to interrupt the flow between Lane and Dana. Now, if I have the opportunity to interrupt the flow between lots of people, then I'm between lots of people, and so I have a high betweenness score. So you can think of betweenness as your ability to interrupt the flow of goods in a network, or the flow of information in the network, or something like that. So in this case, for your star network, the nodes on the periphery, they're not between anyone else, right? So they have no ability to block the flow from anyone else. They're always receivers and never givers. In this case, these nodes on the very end, they're not between anyone else. But this node in the middle, like almost all paths have to go through this node, right? So this person has very high between the centrality and lower centrality everywhere else. Funny little graph. In this case, these nodes on the edge have between centrality 0, like we would expect. But oddly, the highest between centrality is this sort of ring on the outside. These nodes in the middle have lower between centrality. Why would that be? That's Christ, Moody. Why do you call it centrality if the node in the middle has a low value? What's your intuition? Anyone? Please. You're ahead in the back. Yeah.
I have a question.
Yes.
Does between us just look at 1 degree? Just look at
No, it looks at the entire range. Yes. Thank you. You were having an answer.
Yeah, I think that's kind of it, right? Like they have those spokes coming off of them, despite the fact that they're kind of more on the peripheral, like beltway, and not
Mhm.
on in the middle of the city.
And those, so that's exactly right. So these nodes here are the only ones that uniquely sort of trap these folks. The key for these nodes is that they're not uniquely on any path. Like there's a short path from this node to this node, but you could go around this way, or you could go around this way. And all of these nodes don't need to pass through this node to get to anyone else in the network. And so that ability to route around this middle means that there's very few opportunities to block the flow. Please.
So is this different from bridging?
It's exactly bridging. Between centrality is a measure of bridging. Yes, thank you. Good point. Please.
And the centralization score at the bottom
Mhm.
is a reference to the entirety of the network.
Yes.
They're just
Exactly.
centralization.
So the centralization says that this thing is about 18% between completely even and completely star-like. So that was the logic of the centralization score, was to give a 0 to 1 score. So 1 would be a star graph, and 0 would be either a circle or a complete clique. Everyone is exactly the same, and so it's somewhere between the two. The real problem with centralization is that it assumes a single center as opposed to lots. So that's why it's a hard measure to actually interpret. Please.
Are there measures of centrality that incorporate tie strength? Because potentially it seems like maybe you would need that middle person if you really need for certain things to pass through things. If you really, like you might not take that path around.
Yes, absolutely. And so this is the way I've described it here is just using a binary undirected graph. But these measures have been constructed for both weighted graphs and directed graphs. And so you can have a version that says it's not just the shortest path, but it's the shortest number of weighted hops. So it's easier to get from me to you on a freeway than it is on a back road. So you can take that same sort of flow between this in the same kind of way of thinking about it. Raquel, was that a question? No. Anyone else? Awesome. Then please ask these questions. That's the whole point of why we're here. So that's exactly what we should be doing. Okay. So the reason I focus on these three is that I like thinking of them in combination, right? So degree gives you local volume. Closeness gives you your sort of overall reach to everyone else. And betweenness gives you your ability to monopolize flow in the network. Combined, they tell you something really interesting about the position of a node in the network. So for example, if you think about a node that has lots of ties, high degree, the low closeness, well, that means that I have lots of ties, but it takes me a lot of hops to reach most people in the network. So that means I'm isolated in a cluster on my own off on this edge. On the other hand, if I have really high closeness but very low degree, that means I have 1 or 2 ties, but those ties reach people who then reach people who then reach everyone else. And so I'm at the center of the network even though my own volume is low. And that's a unique kind of social position. And you can think about these combinations that way for any network, for any person, for any combination of positions in the network. Make sense? So it's a nice way of thinking about the pattern of ties as distinct from a particular metric. Now there's one kind of centrality that is different from the others because it combines elements of them. And it's known as, in sociology we refer to it as Bonaci's power centrality, which is a flavor of it. There's another one which is known as eigenvector centrality. There's also page rank. These are all the same characteristic. What they do is they take a centrality, which is not just due to my own feature, but to everyone else. Most of you have probably used Bonaci's, you've used the centrality probably this morning I wouldn't be surprised. Does anybody Google anything this morning? No. So Google is an eigenvector-based centrality score. So Google search engine, the heart of it is PageRank. And PageRank is a flavor of eigenvector centrality. And Bonesich power centrality is also a flavor of eigenvector centrality. And the way these work is that the eigenvector centrality, which is defined in this set, is intuitively, the way to think of it is that my centrality is a weighted function of the number of ties that I have and the number of ties that the people I'm tied to have. So if I have 3 and my friend has 3, then I now have 6, right? Or that edge would be weighted 6, this would be weighted 6, this would be weighted 6. Renormalize it, do it again. Renormalize it, do it again. Take the weights by averaging the number of ties I have with the number of ties you have, weight it again, do that over and over and over again. And you end up with people who have really high ties, a really high centrality, if I'm tied to other people who are also highly central. You can think of it, for those of you that this helps, is that it's really much better to be king of the popular kids than to be popular amongst the nerds. Right? So if you were like, many of us were probably on the sort of, I won't speak for you, but many of us become academics because we weren't at the cool table, right? I mean, if we weren't at the cool table, right, we might have been popular amongst the Dungeons and Dragons set, but that's very different than being popular amongst the football set, right? And so popular amongst the popular is what Bonesich centrality gives you. Whereas degree centrality just tells you how many friends you have. And that's the difference. And so eigenvector centrality, Bonesich centrality, that's giving you the weighted effect. Now the reason we use Bonesich power centrality is because Bonesich added this little coefficient beta to this basic notion of what eigenvector centrality is. And this is a radius of how much the network matters. If this beta is equal to the largest eigenvector, or think about it as a scale as big as it can be, then the entire network is taken into account and it's equivalent to eigenvector centrality. If this thing is 0, it's equal to degree centrality. So essentially it's telling you what's the scope, it's a tuning parameter to tell you how much of the network to take into consideration when you're thinking about whether or not it matters. Right? The other nice thing about beta is you can sign it. You can say it can be either a positive score, which is what we've sort of been discussing, or you can flip it and say it's a negative score. If it's a negative score, if you have a negative weight, it says I get more centrality power, I get more power by linking people who are otherwise not linked to each other. And so it bridges between this. So Bonesich is nice because it sort of gets all of these elements together. And if you think about what that looks like, is that on a line graph like this, if I have a sort of a middling weight, so I take this, a pretty good weight, the positive score does exactly what you would expect. The person in the middle has the highest centrality, then a little lower, then a lot lower, and really low at the bottom. But the negative score says that these people in the middle here, they have, these folks right here, they actually have pretty low centrality, and that's because the people on either side of them have the ability to interact with people that they wouldn't otherwise set. So it gets at some of this bridging characteristic. I've yet to find a whole lot of good health reasons for it, but this is really important if you're studying markets, if you're studying what's known as power exchange networks. Negative Bonesich centrality is effectively your ability to exclude trading partners, and your ability to exclude trading partners is the thing that gives you power in an exchange network. So there is a field for which this really matters. I just haven't seen it a lot in the health yet. All right. We're getting behind. I'm going to skip balance theory, because we talked about that already. Triads are my favorite thing in the world, so that's a step, but I'll sneak it back in. You get to hear me a lot today, so I'll sneak this back in later. From a health standpoint, one of the key features that we care about is this thing called homophily. It's probably the single biggest principle that we know in networks. So sick people hang out with sick people. People that are good, healthy exercisers hang out with exercisers. Republicans with Republicans, Democrats with academics, right? So you get sort of this nice sort of selection of homophily, right? We know where things are at. This was the whole point of this discussion, this piece I showed before. Homophily can be structured by lots of things in the feature. It's nice to have a couple ideas about how to measure homophily. And so we measure homophily usually based on some feature of a mixing matrix. And a mixing matrix is just an aggregation of the adjacency matrix, where we've aggregated it by some category. In this case, I've aggregated the adjacency matrix by grade in schools. You have 7th graders, 8th graders, 9, 10, 11, and 12 in this small rural school. And you can see that there are 104 ties amongst the seniors, and there are 192 ties amongst the 7th graders. There's only one tie from the 7th grader to a senior, and one tie back from a senior. Did I symmetricize this? It did, yeah, all right. So we don't know if it was directed or not, because I constructed this network to be undirected. But in this case, we can see there's one link between a 7th grader and a senior, and 22 links between a 7th grader and an 8th grader. So the adjacency matrix is the base data we typically use to construct a homophily score. And the way you construct the homophily score, there's bunches of different ways to do it. And so the simplest possible way to do it would be to say, well, what proportion of ties fall inside the group versus between the groups? So you just take the ratio of the number of ties on the diagonal versus the rest of the ties in the network, and that gives you a nice, easy to interpret, very simple measure. Another version of that is the externalized internalized index, or the EI index. This is the number of external ties minus the number of the balance of external ties to internal ties over the total of ratio ties. So this is essentially telling you what proportion of overall ties on balance are going outside the group versus in. The nice feature of this is it has this nice range between -1 and +1, where -1 means you have a fully exogenous network, and +1 means you have an entirely internal network. Or other way around, sorry, -1 is internal. The simplest measure probably are various versions of what's known as an assortativity index. It's just a correlation coefficient. We say for along the edge, what's the correlation of my grade with your grade for the school as a whole? The beauty of the correlation coefficient or the assortativity indices is that we're social scientists. We've been using correlations like every day for our life. So we interpret it, we know what it means, right? It makes sense. You don't have to worry about these other kinds of interpretations. The problem with all of those measures, the correlation maybe not quite as much, is that it has the compared to what problem. And the segregation index or modularity index are always compared to a random mixing model. And so that's what we typically end up using a lot of the times. So we can take the number of out-group ties or cross-group ties, the observed number of cross-group ties, and compare those by this expected value. So how many would we expect by chance? And the classic version of this is we calculate chance the same way all of us did in our Stats 1 class of calculating a chi-square table. Right? We take the row sum, divide it by the column sum, or times the column sum, and divide it by the total. That gives you the expected. Again, this is like literally Stats 1 chi-square calculation, and so we know how to calculate that expected value. We compare that then to the number that we would expect under that model on the off diagonals, the number we actually observe on the off diagonals. If we get a lot more, then the network is segregated, right? They're breaking up into groups than we expect. An example: imagine you have a little network like this. In this case, you have 2 attributes. You can either be brown eyes or blue eyes, or you can be square. If you're not square, you must be hip. So we have hips and we have squares as an old rock and roll reference for the old farts in the room, right? So you have hips and squares, brown eyes or blue eyes, and you can see that the hips and the squares really are like very far apart from each other. And so in that case, it's a 2 by 2. In this case, there should have been that 30 over there. That moved out somehow. But in this case, the segregation in this network is very low. In fact, there are more cross groups negatives, so there's more cross group ties than you'd expect than you expect by chance. So it's a negative score. In this case, most of the ties, that 30 should be there. Most of the ties are on the diagonal, and so the segregation is about 70. So that tells you this sort of notion that compared to chance, there's lots more in-group mixing than not. The other way to think about homophily, which I think is probably one that you're probably also pretty used to, is thinking about odds ratios. If you've ever done a logistic regression, then you've used an odds ratio. And an odds ratio is nice because it just says that what's the relative odds of a tie within group versus between group. Now, some people don't like the odds ratio, like if you want to think about things like marginal effects. So in logistic regression is having a down moment right now, and sort of in the methods world, for whatever reason. But if you're used to thinking about odds ratios, it's a perfect good way to use it. The advantage of an odds ratio over a segregation index is it's what's known as margin free. I could double the size of the population and it wouldn't change the score. That's not always true with segregation indices, right? Because it changes the denominator a little bit. So the formula is there for this. If you want it, it's for this little network for the hips and the squares. The odds of a within group tie by shape is about 16 times the odds of a meeting between group. That's how you would interpret that measure. Now the final measure in network science that has sort of taken over the idea of homophily or other kinds of mixing is known as modularity. And modularity we're going to go through in great detail when we get to the community detection idea, but effectively it's a normalized version of segregation. Because what you're doing is you're taking your row effect and your column effect, so row times column divided by total subtracted from observed. That's your chi-square, right? It's right back where we started. And that's your expected number of ties, that's your observed number of ties. You do it over all pairs, and you only look at the ties within group. So that's what this is doing. There's this little guy here, which is really going to be a pain in our ass later, but I'll tell you about how that works when we have time to get to it. But the modularity score has this nice feature that it ranges from 0 to 1, usually, or from random to 1. And so it has, in this case, the hips and the squares is about 0.37 in that little example. All right. Questions, comments? That was a lot on metrics. You're going to see a lot of these come over again. I'm going to give you more triad stuff later because I can't help myself, but that's where we're at now. Please.
You can reinterpret the 0.377, like where was that?
No,
Like,
I can't. That's the problem. I can't because this thing complicates the bejesus out of it. But if it were 1, it's essentially your distance towards perfect segregation. So if the value were 1, you would have all ties within groups and no ties between groups. If the value is 0, it's just pure random mixing. Anything less than 0 means you have more ties out-group than in-group. We almost never see a negative value because that would mean heterophily as opposed to homophily. The one case you obviously see it is for heterosexual mixing in a sexual network. That'll have a negative modularity score, but by and large, you're going to see positive values. So I like to think about it as its range from 0 to 1, which is random to complete. And so this is about 40% of the way to complete segregation in this network. Conditional on big asterisks what this little resolution parameter means. So that unlike segregation and unlike odds ratios, it doesn't have a nice numeric interpretation. You just have to think about it as this continuous scale from half empty to complete. Does that help? A little bit? All right, I believe, someone correct me if I'm wrong, the lunch is ready? Yes. So, go back, get your lunch. Most of the time this week, we've got some feedback that the days are a little bit too full. So the next 2 days, tomorrow and the next day, your lunch is on your own. Find a new friend, go have lunch with them, discuss your problems and the problems of network problems, about your social problems, and then and do that. Today we're going to have a lunchtime talk where Dane and I are going to it's hopefully a discussion about the ethics of network data analysis, about collecting data and how you make sense of that. I think Ashton ran out. I saw him a minute ago. I'm going to bug any of you that have collected data. You're going to hopefully engage in this conversation because it turns out that there are some interesting issues that have to do with this fact that all the beauty of networks carries with it a certain set of baggage and a certain set of complications that we need to make sure we're all aware of when we get into it. Okay. All right, so take 10 minutes or whatever it takes to get your food and find your way back to your seat. And